April 20th, 2010. 11 workers died and 17 were seriously injured by an explosion on the Deepwater Horizon, an offshore drilling rig located approximately 50 miles off the coast of Louisiana. The rig burned for 2 days, eventually sinking and triggering the largest oil spill in U.S. history as oil and gas spewed up from the sea floor. The Deepwater Horizon had been drilling an oil well in 5,000 feet of water in an area of the Gulf of Mexico known as the Macondo Prospect. In 2010, the CSB launched an investigation to examine the technical, organizational, and regulatory factors that contributed to the accident. During the investigation, the CSB made new findings about why a key piece of safety equipment, the Deepwater Horizon's blowout preventer, failed to seal the well during the emergency. These new findings help explain why the accident was so devastating, and the CSB cautioned that other blowout preventers currently in use could fail in similar ways. Drilling an offshore well involves creating a pathway between the drilling rig and oil and gas reservoirs trapped beneath the sea floor. A deep hole, or well bore, is drilled through layers of subsea rock and sediment. These rocky layers can contain trapped water, crude oil, and natural gas under pressure. An unplanned flow of these well fluids into the well bore, known in the industry as a kick, can be dangerous. Without careful management, a kick can lead to a blowout, the uncontrolled release of flammable oil and gas from the well. A blowout can be catastrophic, since oil and gas reaching the drilling rig can quickly find an ignition source, leading to a fire or explosion, endangering the lives of the drilling crew. To prevent kicks, drillers pump a dense slurry called drilling mud into the well, creating a barrier between the undersea oil and gas and the piping that leads to the rig. If this mud barrier fails or is somehow removed, the safety of the drilling crew depends on a critical piece of equipment located on the sea floor called the blowout preventer, or BOP. The BOP is a complex electrically and hydraulically powered device that is essential for controlling the well and, in an emergency situation, preventing a disaster on the platform high above on the sea surface. The BOP is connected to the rig by a large diameter pipe called a riser. If a kick occurs, the blowout preventer is designed to prevent flammable oil and gas from traveling up the riser to the drilling rig. This is done by sealing the area around the drill pipe, known as the annular space. To do this, the crew can manually close pipe rams and donut-shaped rubber devices known as annular preventers. If those devices should fail to work, the last resort is a pair of sharp metal blades which form a blind shear ram designed to cut the drill pipe and seal the well. The blind shear ram can be activated manually or by automated emergency systems. At approximately 8:45 p.m. on April 20th, 2010, a kick occurred in the Macondo well. Oil and gas entered the well bore undetected, eventually passing above the blowout preventer and traveling quickly up the riser toward the Deepwater Horizon and the 126 people on board. Just after 9:40 p.m., drilling mud, forced upwards by the rising oil and gas, suddenly blew out onto the rig. Crew members responded by closing the upper annular preventer in the BOP. However, this did not seal the well as intended, and flammable oil and gas continued to flow into the riser toward the rig. Next, the crew closed a pipe ram. This successfully closed the annular space and sealed the well, but tragically this proved to be only a temporary fix. Oil and gas that were already above the pipe ram continued to flow inexorably toward the Deepwater Horizon. As the oil and gas escaped the riser onto the rig, the pressure dropped in the annular space above the pipe ram. But at the same time, the pressure in the drill pipe climbed substantially. The drill pipe was closed at the top, but oil and gas continued to flow in from the reservoir below. After extensive analysis, the CSB concluded that this large difference in pressure likely caused the drill pipe to buckle, essentially bending the pipe off-center inside the blowout preventer. The buckling pushed sections of the drill pipe outside of the reach of the blind shear ram blades. This would eventually prove to be catastrophic. At approximately 9:49 p.m., the flammable hydrocarbons found an ignition source, and the first explosions shook the deep-water horizon. With the drill pipe buckled, the explosion and subsequent loss of electrical and hydraulic power from the rig likely activated an automated system on the blowout preventer known as the AMF Deadman, which closes the blind shear ram and cuts the drill pipe. This emergency system is designed to activate when electric power, hydraulic pressure, and communications from the rig have been lost. The AMF Deadman system was operated by two redundant control systems on the BOP, known as the yellow pod and the blue pod. The redundancy is supposed to increase the reliability of the system in an emergency situation. The yellow and blue pods worked independently of each other and were comprised of identical enclosed computer systems and sets of solenoid valves. When activated, the solenoid valves controlled important BOP functions, such as closing the blind shear ram. If electrical power from the rig was lost, as happened on April 20th, 2010, both the yellow and blue control pods contained backup 27-volt and 9-volt batteries to power emergency functions. The 9-volt batteries powered computers that would activate the solenoid valves, which were powered by the 27-volt batteries. However, evidence indicates the blue pod had been miswired at some time before the BOP was lowered onto the seafloor. This caused the pod's 27-volt battery to drain and made it impossible to operate the solenoid valve for the blind shear ram on the night of the accident. And within the redundant yellow pod, the solenoid for the blind shear ram had been miswired. The solenoid valves were controlled by two coils of electrical wire. These two coils were designed to work in concert, generating a magnetic field strong enough to operate the valve. But within the miswired solenoid valve, the two coils actually opposed each other, leaving the valve paralyzed. Only a third unplanned failure allowed the yellow pod to operate. On the night of the accident, one of the 9-volt batteries that powered the solenoid valve's computer had failed. As a result, the affected computer system could not initiate the command to energize the miswired coil. Had both coils of the miswired solenoid valve been energized, the two coils would have generated opposing forces on the valve. The solenoid valve would have remained closed, and the blind shear ram would never have been closed. However, the failed battery rendered one coil inoperable and most likely allowed the other coil to open the solenoid valve by itself. This in turn initiated closure of the blind shear ram. This should have cut the drill pipe and sealed the well, greatly reducing the impact of the accident. But because the drill pipe was buckled and off-center inside the blowout preventer, it was trapped and only partially cut. With the failure of this last-ditch measure, there was nothing left to stop the massive oil spill and the destruction of the rig. During its investigation, the CSB identified a mechanism that likely caused the drill pipe to be buckled around the time of the explosion. This mechanism is called effective compression. Although effective compression had previously been noted as a hazard in other drilling operations, it had never been identified as a problem affecting drill pipe during well operations. Effective compression occurs because although pipe may appear to be perfectly straight, in fact it has minute bends and irregularities, invisible to the naked eye. Along these bends, the side of the pipe that is curved outward is slightly longer and has more surface area than the other side. When there is a large difference in pressure between the inside and outside of the pipe, as happened on April 20th, 2010, the longer side of the pipe experiences a larger bending force. Eventually, this force can become great enough to buckle even heavy pipe. This is an important finding, CSB investigators said, because the same conditions of differential pressure could occur at other drilling rigs, even if a crew successfully shuts in a well. The CSB warned this could make existing blowout preventer designs less effective in emergency situations. In the case of the Deepwater Horizon accident, the buckled drill pipe prevented the blind shear ram from sealing the well. Oil and gas from the well flowed out of the buckled drill pipe and into the Gulf of Mexico for 87 days. A reported 5 million barrels of oil eventually spilled, causing one of the worst environmental disasters in United States history.